Hello students, in this video we'll discuss Clairaut's PDE, which is a nonlinear first-order partial differential equation. So let's recall the ODE, which was y equals xy prime plus fy prime, was the Clairaut ODE, was Clairaut's equation. Okay. And then what did we do with Clairaut's equation? We differentiated Clairaut's equation. To solve this, we differentiate. Okay. And this is a good example of where an ODE technique will apply to a PDE result. We've already seen this with method characteristics. It still persists a little bit. So if we differentiate this, we get y prime is equal to xy double prime plus y prime plus f prime of y prime, y double prime. And remarkably, the y primes cancel out. And this factors as y double prime, and then times x plus f prime y prime equals 0. Okay, well that's great, because now either one of those two things has to be 0. So y double prime can be chosen to be 0, right? So y double prime is 0, which forces y prime to be a constant a. Well, if y prime is a constant a, then you can write down the solution. Then the solution becomes y is equal to ax plus f of a. So there's a family of lines over here. So this family of lines is going to be the solution to the Clairaut ODE. This is a one-parameter family of lines. One-parameter family of lines. Okay? And we also saw, when we studied the Clairaut ODE, that if I looked at that one parameter family of lines, those formed the envelope, right? The envelope of those lines is itself a curve, and that curve also satisfies the ODE, and it's the singular solution to the ODE, right? So that's beautiful. Now let's extend this reasoning to PDEs. So how would I do that? Let me consider now Clairaut's PDE. So Clairaut's PDE is the following. Well, let's exactly try to mimic this behavior over here, right? So let's look at u is equal to x ux plus y uy. So that's just a first order homogeneous PDE, right? But then plus now, plus an arbitrary function of ux and uy, okay? That's Clairaut's PDE. Very, very similar looking, right? Now I can't do the same sort of tricks over here, but I can easily find a family of solutions just by analogy with Clairaut's ODE, right? So let me consider the two-parameter family. So consider the two-parameter family. I'm going to look at these things over here. I'm going to look at u of x and y is ax plus by plus f of a comma b. That's a family of planes, right? This is a family of planes. Great. And I claim that these planes are the solution to the Clairaut PDE. Let's just formally check it, right? So what would ux be over here? So ux is just going to be what? Ux is just going to be a, uy is just going to be b, okay? So now is it true that ax plus by plus f of ab, is that equal to x times ux? Well, ux is what? A plus y times uy, well that's y times b, right? Plus f of ux, which is a, and uy, which is b. Yeah, it works. Cool. So that two-parameter family of planes are the solutions to the Clairaut equation. But now the interesting thing is that we can think of it exactly analogously. Can I construct other equations, other solutions to this equation using this envelope idea, right? So recall that we can find envelopes. So recall we can find the envelope of a two-parameter family with parameters a and b. by solving these three equations, by solving. So say, for example, your surfaces are z is equal to u of x and y and a and b for your parameters. Then you would have this equation over here, that's equation 1. Then equation 2 you'd have to solve is you have to solve 0 is equal to ua, the derivative with respect to a, x, y, a, b. And then what? And then the third equation would be ub 0 is equal to, so that's a 0. 0 is equal to ub x, y, a, b, right? So there are three equations. I can eliminate two parameters from those three equations, right? And then I'll get the envelope of those curves. Okay, let's see an example of this. Here's an example of how this would work. Let me consider u is equal to x ux plus y uy plus ux squared plus uy squared over 2. Okay? So what are my planes? The solution planes look like what? The solution planes, x and y, look like ax plus by plus a squared plus b squared over what? Over 2. Okay? But that was my family of planes, right? If I do an a derivative, instead of a derivative equal to 0, what's an a derivative going to be? An a derivative is just going to be x, so partial a of this, x plus a. And if I do a b derivative of this, d by db, I'll get 0 is equal to y plus b. So x is negative a and y is negative b. So let's see what we get over here. So if x is negative a, this means my solutions are going to look like what? So x is really, or a is really negative x, right? So my u of xy, my u singular solution is going to be what? Is going to be a, which is negative x times x, negative y times y, and then plus x squared plus y squared over 2. And that's x squared, and that's negative x squared, that's negative y squared. So your singular solution to this set over here, the singular solution, xy, is going to be just what? Just negative 1/2 x squared plus y squared. So that's a solution to the PDE that was not in the complete family, right? And that's what happens in ODEs too. If you recall from ODEs, what we did is we said, okay, here's a nonlinear ODE. And we find a one parameter family of solutions to that first order ODE that was nonlinear. And then when we eliminate that parameter, we found a secondary singular solution which did not arise from that total solution, right? And that's a property of nonlinear problems, that you can have these envelopes that will also work for you, right? In the linear case, those don't exist because those solutions will foliate the space. Now we're in a situation where the solutions do not foliate the entire space, and the singular solution is what is going to be left over when you basically unite all of them. And that should make sense too, because what's the key feature of that envelope? The feature of that envelope is that it has to have the same differential structure as the original solution, so it's definitely going to satisfy the PDE as well, automatically, right? And so you can actually plug this one back in just to check to make sure it works. It will. And that gives a good example of nonlinear structures inducing singular solutions to differential equations. Thank you very much.